The second part of our MATH2 module is about languages. And of course, you can find all interesting details about languages in the book we use, the Shams outline in chapter 12. Well, the first part of the languages is a little bit boring. It's just all about definition. So what do we see as a language? Well, to start with a language, you need to have an alphabet. Yeah, you need to be able to talk about symbols inside that alphabet, and they're called letters. And the alphabet A contains letters, so A is a set having letters inside. If you put these letters in some sort of order, we can call it a word. And then, of course, if we put all these words, possible words, together, then again we have a set. But now a set of combinations of letters. And this collection of words on a specific alphabet containing words is called a language. So a language is just a set of words. So if we have an alphabet containing of only 3 letters, A, B, C, so the symbols from the alphabet A are A, B, and C. Then you can make connections of these letters forming words. If we define a language, then we say, okay, within this language, the following words are allowed. So if we look at L1, then the words AA, AB, ABC, and ABA are allowed words in that language. And so you can make an enormous amount, an infinite amount of languages containing of words built with the help of the letters of an alphabet. If we look at another alphabet, we have the alphabet A containing the $ A and B. Then again, we can all make possible combinations of these 3 letters to form words. So if we look at A3, then we can also say this is just AAA. It's just a shortcut, an abbreviation to help us save some typing and some writing. Of course, we also can have a word without any letters, and this is called the empty word. And it wouldn't be math if we wouldn't have defined some symbol for this. So the empty word is defined with the symbol lambda or epsilon. And the empty word is a word in a language. So if we have a language A containing the empty word, then that is a language with exactly minimal 1 word in there, the empty word. If we look at A0, then of course that means we have no A's consecutive. That would be exactly the same as the empty word, lambda. So try to write this one completely. Okay, that's quite easy. So we have AAA, lambda, and we can of course drop the lambda because lambda is the empty word. So we could omit this one. And then we have between brackets A, B square, C, and that in total square. So if we try to figure this one out, this would mean AAA, ABC, and then again ABC. Then we have CB to the power of 0, which is the empty word again, so we can omit it, E. So the total one would be AAA, ABBC, ABBC, E. If we look at the number of letters in the word, then that is called the length of the word. And the notation is the one you already are familiar with in the set theory. So the straight lines with a word in between, or you can use the letter L for the word. So if we look at the length of AAA, that of course is 3. The length of $AA, it's 3. And the length of BB dollar is 3. Well, the length of the empty word is of course a special case. In the empty word there are no letters, so the length of the empty word would be 0. If we look again at some expanding things, so we have there a very complicated word containing of zeros and ones with a lot of powers in there. Then if we try to read it, it would mean 001, 001, 001. The first thing would be placed 3 times. Then we have 0111 twice, so again 0111. And then the complete thing would be multiplied with 4. So if we calculate the number of letters, that would give us 3 times 3 for the first part, 2 times 3 for the second, 2 times 4 for the second part, and that in total times 4. We still have some special definitions. For example, A star is a set of all possible word combinations, all possible words, so all possible letter combinations on an alphabet A. So a language L is just a subset of this A star, because A star contains all possible words, and in language L is defined with a restricted number of words. So L would be a subset of A star. We can also have some operation on words. For instance, we can concatenate. So if we concatenate AB and ACB, we would get AB, ACB. If we concatenate with a lambda, the empty word, that would result in the same word. So lambda concatenated with ABA would still be ABA. And of course, this operation would also apply to ABA lambda. Lambda is an empty word, so you can omit it, you can put it in as often as you like. If we look at the two questions, commutative, associative. So would concatenation be commutative? Well, of course, no. So if we put AB and ACB together, then we get AB, ACB. But if we would do ACB first and then AB, we get quite different words. So it's not commutative. Is it associative? Yes, that is. And so if we put AB and ACB and then again a third word together, I don't care whether you put the first two together first, then the second or third one, or the other way around. So it's not commutative, but it is associative. Some other definitions, we can look at subwords. So subwords is just the number of letters inside a word, consecutive. So you may not have empty spots in there. So if we look at ABBA, the word ABBA, then BBA would be a subword, or AB would be a subword, or BB, etc. So ABA is not a subword because we don't have consecutive letters in the original word with form ABA, which would form ABA. If the subword starts from the beginning, we call it an initial segment.